In 7.1 to 7.4, you learned about the various ways you could solve a system, which includes solving by graphing, solving by substitution, or solving by elimination. Now you're going to take those methods that you've learned and you're going to solve systems that might have special types of solutions. And in this case, you might have a system with one solution, which is really what you've been seeing all along so far, no solution, or an infinite number of solutions. And we've seen similar things to this back in chapters 3 and 6. The second goal that we're going to do is we're going to arrange systems so you can identify the number of solutions without actually solving them. So the first thing we have to talk about is what a solution to a linear system actually is. So in a graphing sense, if you're going to graph two lines, the solution is going to be the point of intersection or the point on both lines. So keep in mind that each line that you graph has an infinite set of points on it, but if lines intersect, they're going to have one point in common, and that's your solution to the system. The other way to think about a solution is an ordered pair that when you plug it in, works for both equations in the system. Or if you had 3 equations, it would work for all 3. So we're going to be talking a lot about these different situations, and you'll see it reformatted and kind of rementioned and reorganized in various different ways. So when you graph two lines, you can actually end up with parallel lines, and we know that parallel lines don't intersect. So if two lines don't intersect, and a solution is where the point of intersection, well then that system would have no solution. And we know that lines are parallel when their slopes are the same. The other thing, though, is that their y-intercepts, which is b, has to be different. And the reason for that is because if they had the same slope, and then the y-intercept would also be the same, they would be the exact same line. It would be like graphing a line and then having another line directly on top of it. So again, if you think about solutions being the point of intersection, these two lines that I drew over here, not very accurately, but they intersect an infinite number of times. So they're actually going to have an infinite number of solutions. And in terms of slope and y-intercept, they would have the same slope, but then their y-intercepts would also be the same. So they're the exact same line. So then if two lines are not parallel, then two parallel lines never intersect. When lines are not parallel, it just means they're going to intersect. And since lines are straight and they don't bend, they're going to intersect once. And two lines are not parallel as soon as their slopes are different. It doesn't even really matter about the y-intercept. So down here, you're going to solve these 4 equations and inequalities. These are actually just a recall from chapters 3 and 6. So solve those, say your solution, pause the video, and press play when you're ready to check your answer. So after solving each of these, here you end up with 12 equals 16, which it doesn't, so your answer is no solution. Over here you end up with 24 equals 24, which it does, so you have all real numbers could be your solution. So here, x can't be anything, there's no number that would work, and over here x can be anything, no matter what you pick, it's going to work. Just a good habit, don't stop at these points, even though here you can probably see they're definitely going to be different, and here you can see they're exactly the same. You actually want to minus 3x from both sides, and here you actually want to minus 8x from both sides. Down here you get 6 is less than 10, which is true, so all real numbers, and negative 3 is greater than negative 2, which is false, so no solution. Regardless of if you're doing an equation or an inequality, what we've learned to this point is that if you get a false statement, we've been saying no solution, meaning there is not a solution. And if we get a true statement, back in chapters 3 and 6, we would say all real numbers. That language, the all real numbers, is going to change a little bit now that we're in this section of systems, but the no solution will stay the way it is. So in this first example, it says that we can solve by the method of our choice, so that means we can either graph, substitute, or eliminate. Chances are you're not going to choose graphing unless I force you, so for these 4 examples here, we'll assume we're not going to graph. We're either going to substitute or eliminate. Since these 2 equations are already stacked and they have matching coefficients, I'm going to eliminate by subtracting. So 3x minus 3x is 0. 2y minus 2y is 0. So if I bring down my equal sign straight down, I'm left with 0 on the left, and then 10 minus 2 is 8. 0 doesn't equal 8, so that's going to be no solution. Over here, on this one, so we've kind of already eliminated graphing as an option. So you could eliminate to solve this system, but to do that, you'd have to stack your equations first by minusing 1/2x to the left. and then you'd also have to get your coefficients to match. So it would actually be a two-step process before you could even eliminate. Since y is already isolated, and that's the first step of elimination, is to isolate any, or substitution is to isolate any of the variables, I'm actually going to use substitution and replace y in the first equation with 1/2 x plus 2, and then bring down everything else. So then if I distribute a -2, I have x minus 1x minus 4 equals -4, but then x minus 1x, that's 0, so that goes away. So I have -4 equals -4. And since that's a true statement, we used to say all real numbers. I'm going to actually talk about on lower in this slide why we won't say that anymore, but what you're going to say for your answer is infinite solutions, because that's how many solutions that system has. Pause the video and try these two using the method of your choice, and press play when you're ready to check your answers. So on the first example here, they're already stacked, they're already matching. It makes the most sense to eliminate, and you can eliminate by adding. So 5x plus -5x is 0, 3y plus -3y is 0, so that's what you're left with over here. And then 6 plus 3 is 9. 0 doesn't equal 9, that's a false statement, so you say no solution. Over here, you could eliminate if you wanted to, but you'd have to bring your y over and then multiply your top equation to make them match. Or, since y is already isolated, you can replace y here with 2x minus 4. So I substituted. So then you're distributing 3 to both 2x and -4. Then your -6x plus -6x goes away, and then -12 equals -12. Since that's true, we're going to say infinite solutions. So down here, we're going to solve by graphing. Again, you probably only choose this if I made you, which I am. So when you graph, you have three choices. You can graph by making a table, which almost no one chooses. You can graph by using x and y intercepts, or you can graph by using slope-intercept form. This example right here, since it's in standard form and the intercepts are both good, I'm going to graph by using x and y intercepts. I'm also just going to put a red dot next to here so you know on my graph that's my red line, and I'm going to put a blue dot next to here so you know that that's my blue line. So to find intercepts, you change the opposite coordinate to 0. So if I make y 0, that would drop out 2x equals 6, so my x-intercept is 3. And then if I make x 0, I'd have -3y equals 6, so my y-intercept is -2. And then I'm going to connect that with a line. Now the next one's a little bit tricky. It looks like I'd want to use intercepts, and if I did that, I can see I have an x-intercept of -2, and then I have a y-intercept of 4/3. So 4/3 really isn't easy to graph, but an x-intercept of -2 is really easy, so I can graph that. So rather than trying to graph 1 and 1/3 for my y-intercept, what I would do is I'd actually take this equation and put it in slope-intercept form. So I'm going to minus 2x from both sides, and then divide by -3. So in slope-intercept form, we already knew the y-intercept was 4/3, so it's good that it came out that way, and I change that to plus negative, so I get plus 2/3 x. So in doing this, I have my slope, which is 2/3, so I can actually use that to get from my x-intercept that I already have graphed to my next point, because slope just tells you how far away the next point is. So my next point is up to over 3, and I'm going to put a dot right there, and then I could do that again, up to over 3. And I could do it again, up to over 3, and I could go some backwards, and then I could connect with a line. So now that I've graphed, I can see that I have parallel lines, which means they're never going to intersect. If they're never going to intersect, they're never going to have a point in common, so I'm going to say no solution. If I come over here to this example, now I'm going to graph these two lines. So again, I'm going to do this one in red, and I'll do this one in blue. So the top one, it's set up for intercepts, so my x-intercept would be 2, and my y-intercept would be -4. I'm going to connect that with a line. And then my blue line, it's in slope-intercept form, so that's the method that I'm going to use. I'm going to start down 4, and then I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. So you can see that if I connect this with a line, that it's going to become the same thing. And so this is where you'd say infinite solutions, because the red line and the blue line will intersect infinitely many times. They have infinite points in common. Any point on these lines is a point on both lines. So the reason that we're avoiding the words all real numbers is because all real numbers means that the answer can be anything. But if you just kind of take a look at the graph, for example, that's a point on the graph, but that origin actually is not a solution to the system, or any of these points over here. So we really want to avoid saying all real numbers, because it can't be all of the ordered pairs. Not all of them are solutions. There just happens to be infinitely many of them. So in this slide, we're not really going to say anything new. We're just going to organize the information that we've already talked about a little bit. So a system of equations is going to have no solutions when two lines are parallel, because parallel lines never intersect. And we know that two lines are parallel when their slopes are the same, but also that their y-intercepts are different. So I'm actually just going to take that information and I'm going to put it right down in this chart down here. So one possible number of solutions is no solution. And for that to happen, the slope has to be the same, but the y-intercept has to be different. And the reason for that is because if they were both the same, then the system of equations would have an infinite number of solutions because they would be the exact same line. And lines are exactly the same when their slopes and their y-intercepts are both the same. And I'm just going to write that down here as well. And so then the last possibility is that a system of equations will have one solution. That happens when two lines are not parallel, because lines can either be parallel or they're not. And two lines are not parallel as soon as their slopes are different. Because as soon as the slopes are different, they're not parallel. As soon as they're not parallel, they're going to intersect. So I'm going to put that down here. So it's possible to have one solution when the slopes are different. Now, the y-intercept could be the same, the y-intercept could be different, it really doesn't matter. If it was the same, that would actually just mean the y-intercept is the point of intersection. If it's different, they just intersect somewhere else. So the next thing that we can do with this is, because up here we have all this information about slope and y-intercept, if we can quickly look at the slope and y-intercept, then we can just decide if lines are going to, or if a system's going to have one, none, or infinitely many solutions. So to be able to do that, what you need to do is you need to have the equation written in slope-intercept form. Because if it's in slope-intercept form, then you can just pick out m as a coefficient of x and b as the number that's being added or subtracted. So down here, when it says without solving, it really means don't graph, don't substitute, don't eliminate. All I want to know is, based on the slope and the y-intercept of each line, is it going to have one solution, no solution, or infinitely many? So this first one right here, if you put it in slope-intercept form, you have y equals negative 2 minus 5x. So the slope of the red is negative 5, and the y-intercept is negative 2. If I wanted to get the next line in slope-intercept form, I would add 10x and then divide by negative 2. So I'd have y equals negative 2 minus 5x. I'd have the same thing. I'd also have a slope of negative 5 and a y-intercept of 2. Everything's the same, meaning they're the same line. So they are the same. They will intersect infinite times. They have infinitely many solutions. So in this example here, you're going to try to identify the number of solutions, either one, no solutions, or infinitely many, by analyzing the slope and the y-intercept of these lines right here. Pause the video, press play when you're ready to check your answer. So when you isolate y and put them both in slope-intercept form, the first line becomes y equals negative 3x plus 3 over 2, and the second line becomes y equals negative 3x plus negative 5 over 2. So their slopes are the same, they have the same slope, but they have different y-intercepts, which means they're going to be parallel lines. Since they're parallel lines, they'll never intersect. Since they never intersect, there's no solution. Same idea here. You're actually just going to take each of these three systems, you're going to analyze their slopes and y-intercepts, and decide how many solutions that system has. And then when you're finished with that, you can actually just come down here. These graphs are just asking you to, here you're going to draw a system that has no solution, here you'll draw one that has one solution, and here you'll draw a system that has infinitely many solutions. Pause the video and press play when you're ready to check your answers. So in the first example, here are the two lines in slope-intercept form. They have the exact same slope and the exact same y-intercept, so they have infinite solutions. Here are the second two in slope-intercept form. They have the same slope of 9/5, but different y-intercepts, so they would be parallel, no solutions. And then down here you have different slopes. It really doesn't matter what the y-intercepts are at that point. As soon as the slopes are different, they're going to be intersecting lines. Intersecting lines will intersect once. And then down here, here's just in various examples. Yours might look different. These lines will never intersect. These lines intersect once, and you can see there's a red on top of a blue there.